Hi everybody, welcome to the video. This is for section 2-4 in Math 3 Accelerated. We are looking at, this is the warm-up for 2-4, so it's the front of your notebooks. I'm going to do one example with you, and then I'm going to have you pause the video and do the rest yourselves. So I'm thinking we'll probably do, so we're looking at your basic correspondence, so I'm actually going to do maybe a couple. So I'll go ahead and do 3 and 1. And 7, just I'm going to give you hints on these two and do this one. So this one, I have a base of 3, and we've done exponents before. So I need to rewrite this so the base is 3. So 3 to what power is 243? It turns out it's to the 5th power. You can double check that for me if you want to be sure that I'm not crazy, or so that I know that I'm not crazy. But anyway. So that means because the bases are the same, the exponents must be. So x plus 4 must equal 5, and therefore x is 1. And I found that, again, by using the fact that the exponents have to be equal if the bases are the same. So the same thing applies to logs. If I can take them and rewrite them. So like this one, you'll notice they've taken b and moved it so that they added log base 2 to both sides. I'm going to leave that one, so I actually will do 7. On 7, it's a little different. How will I get a one-to-one correspondence? The base of both of these is 10, so we already have the same base on the logs. Our one-to-one correspondence will come from if we cross-multiply. So then I will have the log base 10 of 2x equals log base 10 of 14. So the arguments have to be equal to x equals 14. And x is 7. I'm just going to not write that down. There's not enough room. So go ahead again and pause the video right now, and I'll have the answers for you. Please try to pause before you get there. Okay, so here are the answers to our warm-up, and I didn't show my work on questions 2, 3, 4, or 7. 4 is really straightforward. 7 we did on the previous page, and 2 and 3 I was able to figure out by looking at the problem. So I did show all the work I did. But you'll notice on number 5 that I showed the statement I came up with after moving this log to the other side, the statement I came up with, and then not how I got to my answer. Same thing for 8. On number 9 is actually a double whammy. When you move it over, you end up with this statement, which is a double problem. So I'm like duplicating the first row. And so I did go ahead and show all of my work for number 9 because it was a little bit more complicated. So talk with each other. If you got anything wrong, check in with one of the 2 adults in the room and see if they can help you. Otherwise, you can talk to me about them tomorrow. All right, so going back to Abe and Mary, so this is the start of 2-4. They're feeling really good about their log rules. They were actually bragging about their great work to their other friend. And so Stephen, their other friend, says, I guess you think you're pretty smart. You should figure out some log rules. But I want to know what they're good for. What's the point? And Abe's like, well, I've seen a lot of times when equivalent expressions come in handy. Sometimes you write an expression with a variable in it in different ways and it means something different. So what are some examples from your previous expressions where equivalent expressions were equal? I'm going to go with my clever form of 1. We have 1, which we can write as lots of things. We found that to be extremely useful, different forms of 1. So that's one example. See if you can come up with some. Remember, some means at least 3. I provided you with 1. See if you can come up with a couple more. And then be prepared to share those with me when I see you next. All right, so Mary goes back to thinking about where we started with logs in 2-1, where we're trying to estimate and order numbers. And maybe there's a way to use our log rules to take values we know and use them to find values we don't. For example, let's say I wanted to do the log base 2 of 6. We know the log base 2 and 3 are that we could use the product rule. And we could say the log base 2 of 6, which is equal to the log base 2 of 2 times 3, which is equal to log base 2 plus the log base 3. And Stephen's like, well, that's great. I know what the log base 2 is of 2. It's 1. But what's log base 3? And Abe's like, I kind of remember that. And so he pulls this answer out of nowhere. So we know you don't know that, and it's bizarre. But he tries it, and he gets this. And This is his answer. Now, based on what we know, is this a reasonable answer? So let's think about that for a minute. What we know about logs is that the log base 2 of 6 is between the log base 2 of 4 and the log base 2 of 8, which is between 2 and 3. So we know the answer is between 2 and 3. That number is between 2 and 3. So it's a reasonable value just based on that alone. It's pretty much in the middle of those two, 4 and 8, because it's 2 away from 4 and 2 away from 8. So it's right in the middle. We've got about 2.5. So that's another reason why it's good. So, but this alone is a good enough reason. It's not great, but it's good enough. So Stephen goes on and goes to say, hey, cool, I've got one, the log base 2 of 5, which must be the log base 2 of 2 plus 3, so I break it apart. Is he right? Or can they both be right? Who's right and who's wrong? Stephen did it this way with plus signs, and Abe did it that way. Okay. So can they both be right? And of course they can. The log base 2 of 5 cannot be equal to log base 2 of 6. Decide who's right and who's wrong. So I told you somebody has to be wrong. And let's talk about it. So Stephen actually applied the rule that Abe first thought was going to work, which was distributing. And you can't really do that. Also, if you think about this, yes, 5 is going to be between log base 2 of 4 and log base 2 of 8, just like this, but it's much closer to 4. And so being right in the middle doesn't make sense. So this is actually not the log base 2 of 5. We will talk more about why. Make sure you're writing stuff. Right. I'm not going to write your explanation for you, but Mary is the one who's right, or Abe, the previous problem with the times in the side, because we know we can't distribute a log across addition. So let's see if we can try it now. So I'm going to give you some values. So we have these numbers up here. The log base 2 of 3, like I said, that was a correct number. It's crazy that they got it from nowhere, but it's correct. We also have the log base 2 of 5 and the log base 2 of 7. And we still have all our knowledge that we already know about log base 2 of any power of 2. The powers of 2 are still going to work. The log base 2 of 2, the log base 2 of 4, the log base 2 of 8, those still all exist. So we're going to use our 3 rules we have to help us. Okay, so the log base 2 of 9 can be rewritten as log base 2 of 3 times 3. Then using our product rule, log base 2 of 3 plus log base 2 of 3. So since I have this, I can then rewrite each of these as 1.585 plus 1.585, which is going to be, use a calculator, and I'm not going to grab a calculator right now and use that, but you'd use a calculator and add that together. So we can use a calculator. I know some of you have calculators that will do log of any base, but you are going to be required to do this work on a test, so make sure you know how. So I'm going to actually leave you to do 5 and 6 and look at 7. 7 is this very large number of 486. I'm going to go ahead and try to break that down. I am using a calculator right now, just kind of doing some quick division on 486. I'm going to divide it by 16, I think. Nope, so we're going to go with 8. Should not go in. So 486 divided by 2. Okay. So 486, so I've got log base 2 of 243 times 2. And 243 is 3 to the 5th power. So I have the log base 2 of 3 to the 5th power times 2. Now I'm going to break that apart. Log base 2 of 3 to the 5th power plus log base 2 of 2. This is 1. This becomes 5 times the log base 2 of 3. And then I would plug this yellow number in here and times it by 5. So 5 times 1.585 plus 1. And again, I'd grab my calculator to figure out that answer. So go ahead and again, pause the video, figure out 5 and 6, and I'll have answers for you in just a minute with calculators being manipulated. Okay, so as you can see, I've grabbed my calculator. I've got 3.170 here on the first number 4, and then on number 7, 8.925. And then on these, I've broken this one apart as 2 times 5, and this one is 4 times 3. You can do 2 times 2 times 3 and do more math, but I made it simpler. And so those are my answers, and that's how I can use them. So these are pretty cool shortcuts. Again, you will need to know how to do this on the test, regardless of what your calculator can handle for you. Okay. Then there's a couple more to try. 8, 9, and 10. So based on what we know, what other values do we need to figure out the value of log base 2 of any number? So go ahead and again and do 8 and 9. I'll get you the answers for those in just a minute, but see if you can figure out the answer to question 10. Stop and think about that. So what kind of numbers do I need to know? I, of course, have all the powers of 2, but then I would need all the possible choices that I get. And so what are some of the numbers that I must know to make this work? It's kind of your question. So keep thinking. I'll be back in a moment. So show my work for number 8 because there wasn't really enough room. And so I've broken up, this is 30 and 7, so the minus sign in between. And then 30 I've broken up into 2 times 3 times 5. And I've strung out my plus signs up here without writing log base 2 of 2 plus log base 2 of 3 plus log base 2 of 5. I just didn't write that step down. So, and there's my answer there of 2.1. And then over here I've got the answer of 1.222. Given the work we've just done, what do we need to know? We actually need to know every single prime number. So if we have, because basically what we're doing here with 30 specifically is we're factoring it into primes. And as long as we have all the 2's, we've got all the 2's we need, and so we just need every prime number, which is a very frustrating potential. So long before there was this, before there were calculators, there were tables, and that's what was in the tables. It would be the log base 2 of all the numbers. So prime numbers, and then you could play these games. So that's the kind of work they did before my time. So let's talk really quickly about these. We're trying to decide if they're always, sometimes, or never true for 11 through 17. So always, sometimes, or never true. If it is always true, we're all set. If it is sometimes true, we need to decide when it is true. So let's pick one that might be sometimes true. I'm not seeing a sometimes here. I'm seeing a couple of nevers and some always. I don't see any that are sometimes, but I'm going to pause and think and write down my answers. And you go ahead and talk with each other, decide. You're going to want to pause the video and then come back to the answers, but make sure you take the time to discuss with each other what you think. Okay, so I have my answers. 11, 12, 14, and 16 are always true. 13, 15, and 17 I said were never true. Now, on these 3 problems, I suppose there might be a value of x that might make them true, and so that would be a sometimes situation, but I cannot possibly come up with that answer right now. So I'm going to leave them as never because these are mistakes that are made all the time that need to be not made. You cannot go across a plus inside the log here, and you cannot take 2 logs and then end up with 2 logs. When we chop a log, we start with 1 log and make it into multiple pieces. We will never have 2 logs from a chop. So like here, the 2 logs, that's again going across the minus, like this is going across the plus, and these are common mistakes that I want you not to make. So I hope that this video was helpful. Again, you want to pause quite frequently as you're watching it and make sure you think about what you're doing and keep in mind what's going on. So I hope you have a great day, and I'll see you all soon.